This is problem 15 in the QHack 2023 Quantum Coding Challenges, and this one is entitled Sub-Superdense Coding. And what we're being asked to do in this problem is to modify the conventional superdense coding protocol so that instead of encoding 2 classical bits in 1 qubit, here we want to encode 3 classical bits in 2 qubits. Now, let's go ahead and first do a quick recap of how the conventional superdense coding protocol works. So the idea is that Alice has 2 classical bits. Here we denote them as I and J. And the whole point of this protocol is that we can encode those 2 classical bits into only 1 qubit that she can then send to Bob, and then he can perform some unitary operations to decode here exactly what I and J are. Now, obviously, it's not as simple as this. For this protocol to work, Alice and Bob need to actually share a pair of entangled qubits. So these qubits can be prepared by a third party and then sent to Alice and Bob ahead of time. And then Alice can perform her operations in her qubit and then send it to Bob, which he can then perform some operation to decode the information. Now, the critical part here is that Alice is only sharing 1 qubit with Bob, and she managed to encode 2 classical qubits. So that's why we call it superdense coding. Now, the pair of entangled qubits that Alice and Bob share are prepared in the form of a Bell state, so an equal superposition of state 0, 0 and state 1, 1. So what operations can Alice perform to her qubit to encode this information? Well, if she performs this type of operations where whenever qubit J is 1, she applies an X gate, and whenever qubit I is 1, she applies a Z gate, then we get the following encoding. So if I and J are 0, 0, it's like she's not doing anything, so it's applying an identity gate. So our state is just the original Bell state. Now, if we have 0, 1, then we apply an X gate to the J qubit. So then this Bell state now changes to 1 over 2, 0, 1, 1, 0. And then if we have 1, 0, then we apply a Z gate to the qubit. So we get the Bell state 0, 0 minus 1, 1. And lastly, if both of them are 1, we apply both a Z and an X gate. So we get 0, 1 minus 1, 0. Now, obviously, if Bob now performs the decoding of these 4 possible Bell states by just applying the reverse circuit that was used to prepare the original Bell state, well, that just results in a state that matches the classical bits that Alice had encoded. So Bob gets state 0, 0 if Alice had 0, 0, and then 0, 1 if Alice prepares 0, 1, and so on. So now in this problem, we're asked to do the same thing, but for 3 classical bits. So now we need to figure out how would Alice encode these qubits and what would Bob need to do to decode them. So if we take a look at what is done for the traditional superdense coding, Bob used the reverse circuit that we had to prepare the entangled pair, right? So we could say if the state that we're preparing here is a GHZ state, which we use this type of circuit to prepare, well, we can say, okay, well, Bob maybe can use the reverse of that to decode what Alice is trying to send him. And then we can ask, well, what are the states that we need to have then at the input of Bob's decoder so that when he applies this circuit, he gets the states that match the classical bits that Alice is trying to encode? Well, that's just the GHZ basis states, which are given by this expression. But to make it a little bit simpler, what we can do is apply here all possible basis states that Bob wants to obtain to this GHZ circuit and see what we get here at in this case, the input, right? So let's go ahead and do that here with this code. So again, we have on here on the left is what Bob wants to decode, which are all possible states 000, 001, 010, all the way to 111. And we want to know, well, what do these states look at what would be his input, right? So what I have here is just a for loop that is going to iterate over all possible states, and then it's going to generate those superposition states. So here we see that if Bob wants to use this circuit, for his output state being 000, he must receive just the original state that was prepared. Now for 001, we can see here that what we need is, if the last qubit is the one corresponding to Bob's qubit in this entangled state, well, what would Alice need to do to her two qubits to encode the state 001? Well, she would have to flip both qubits, right? So considering this is Bob's qubit, right, we can see that with respect to the original state that is prepared, the two qubits Alice has have been flipped. So she needs to apply X gates to both of them. Now, for state 010, right, so the third state here, we see that, again, if this is Bob's qubit, what would Alice need to do to her qubits? Well, she would need to leave the first qubit alone, and then to the second qubit apply an X gate, right? And then we can continue this process and see that for the next one, Alice will have to now apply an X gate just to that first qubit. And then for the fourth one, we can see that when Bob wants to decode state 100, he needs to receive this state where the phase has been flipped. So Alice needs to apply a Z gate to one of the two qubits. Either one should be fine. And then we can continue this process. Now, we can generate a table of what that encoding process needs to look like. And here's what it is, right? So if Alice wants to encode state 000, she does nothing to those qubits so that Bob can receive the original equal superposition state that was prepared. When Alice wants to encode 001, she applies X gates to both of her qubits. So that way we see here they get flipped. For 010, she only applies an X gate to her second qubit, right? So here we can see that only that second qubit gets flipped. And then we can continue the process to see what are the gates she needs to apply. So let's go ahead and get this coded in PennyLane. So as always, we import PennyLane as QML and NumPy. And then what I'm going to define here is the encode function we need given those three classical bits I, J, K. And all I'm doing here is what we just summarized in this table. So do nothing if we want to encode 000, apply X gates to both qubits. If it's 001, then one X gate when this is 1, and then so on and so forth to match that table we had. Now, the function we need to decode, or that Bob needs to decode, again, is the reverse function that we have to prepare that GHZ state. And then we can define our Q node by using a device with 3 qubits, and then the following circuit. First, the preparation of that GHZ state. Then I just have a barrier so that when we draw the circuit it's easier to understand. Then the encoding done by Alice, and then decoding done by Bob. Let's now draw our circuit for, let's say, an input 000, right? And then let's print the output of that circuit. So here we can see that when the input is 000, here in between these two barriers, we're doing nothing, right? We're passing identity. And then Bob is decoding state 000, right? Now, if we pass state 001, Alice applies X gates to both of her qubits. And then Bob is decoding state 1, which is 001. Let's now do 0, 1, 1. In that case, Alice only applies a qubit to her first qubit, and then we get state 0, 1, 2, 3, which is in binary 0, 1, 1. So Bob is decoding the correct qubit. And just for fun, let's just do 1, 1, 1 here. And then we can see here that Alice has to apply an X gate and a Z gate, and Bob is decoding state 7, which corresponds to 1, 1, 1 in binary. So that's it. Please let me know if you have any questions.